Hi, Astronomy. Here's Mr. Janowski. This is the second part of the Chapter 3 slides. So, in physics, who is Mr. Misconception, and what were his two types of motion? That is Aristotle. Aristotle, yeah, he proved the Earth was round. He had evidence-based arguments for that. But in physics, he had lots and lots of misconceptions, and his ideas about physics were wrong. And anyhow, Aristotle believed in two types of motion: natural, meaning it is just of the nature of the thing to do that kind of motion, and violent motion, which is imposed motion. So, who came along and disproved Aristotle's ideas about motion? That would be Galileo. So, about 17 or 1800 years after the time of Aristotle, Galileo came along and he did his experiments with the balls going down the ramp. And what happens in the middle of the ramp shows that you don't need a force to keep an object in motion, which is known as the law of inertia. If it disagrees with experiment, it's wrong. So that's from the Richard Feynman video we watched. That is the key to all of science. In science, you have to check your ideas against the universe. And if the universe tells you that your idea is wrong, well, the universe is correct and you are wrong. That is how it works in science. That is what makes science science. You're checking your ideas against the universe using an experiment. And sometimes the universe will tell you that you're wrong, and you have to accept that. So, what is the tablecloth trick all about? The tablecloth trick is the absolute best example that there will ever be of Newton's first law of motion, the law of inertia. So, this is just Galileo's idea that if an object is at rest and there's no net force on it, it will stay at rest. If the object is in motion and there's no net force on it, it will stay in motion in a straight line, constant speed. So, that's Newton's first law. So, thinking about gravity, Newton is not the first person to attempt to discover and define the force that holds the planets in orbit around the sun. Kepler, before Newton, realized, okay, well, there must be a force doing this. He thought it might be something like magnetism, so he was wrong. He got his laws of orbital motion correct, but he was wrong about this one. And Newton's contemporary and rival, this is the guy that Newton really didn't like, Robert Hooke. He actually suggested that gravity was the thing doing it. And he did this years before Newton actually said so. So why do we consider this to be Newton's idea and not Robert Hooke's idea? I mean, Hooke had the idea first, so why isn't this Hooke's idea? There's good reason for this, and the reason is basically Newton gets the credit because he did all of the math, and he figured out exactly how it should work. Hooke kind of just had a guess. Newton figured out all the details, so this is really Newton's idea. So Newton, in 1687, published the first edition of this book called the Principia, or Mathematical Principles of Natural Philosophy, or in Latin, Philosophiae Naturalis Principia Mathematica. So this is a hugely important book in science, but also in the world. This is kind of what gets the scientific revolution and everything that came after it going, is the Principia. So in the Principia, Newton published his law of gravitation, and he also published his three laws of motion. And these laws together, the law of gravity and the three laws of motion, allow astronomers to predict the position and motion of planets and other astronomical bodies. So if you remember last chapter, when they were looking at the orbits of Uranus, and they realized it wasn't doing exactly what they thought it should be doing according to Newton's laws, they used Newton's laws to predict, well, there must actually be another planet out there tugging on Uranus with its gravity. They used Newton's laws to predict exactly where that planet should be. And literally the first night they looked for it there, they found it. This is a huge win for Newton's laws. They made this very, very bold prediction. And the universe didn't say that, no, you're wrong. The universe actually said, okay, no, you got that one exactly right. Huge win for Newton. So here we're looking at a picture of a tree. And in the background is a house. Well, that is Isaac Newton's house, and that is Isaac Newton's tree. That is the famed apple tree. So we've been over this in class. I'll just say it quickly. The whole, you may have seen a comic showing, an apple falling from a tree, hitting Newton on the head, and that's what, that bonk on the head gives him the idea for gravity and everything else. That's not exactly true, but it is actually partially true. Newton said this in his life to different people who were talking to him. This guy wrote, a biography of Newton, William Stukeley. And Newton himself said that, he got the idea from gravity by seeing an apple fall from a tree. Didn't hit him in the head, but he saw an apple fall, which is a perfectly ordinary thing to happen. Things fall from trees every once in a while. The kind of flash of insight he had is, okay, I expected that to happen, but why did I expect that to happen? Why is that always what it does? Why does the apple always descend perpendicularly to the ground? Thought he to himself in his contemplative mood. So I said I would do this slide quickly. I have failed to do it quickly. But yeah, apple falling from a tree didn't hit him in the head, but it did actually happen. And that was, Newton's inspiration for this. So now we come to this idea of Newton's cannon. So imagine that we have a cannon up on a mountain, or a hill at least, and it's going to shoot a cannonball out sideways, perfectly horizontal, parallel to the ground. So the cannonball is going to leave the cannon, it's going to go a little bit, and it's going to fall to the ground. If it left the cannon a little bit faster, it would go a little bit further before it reached the ground. So far, so good. What Newton realized, this is a thought experiment, he didn't actually do this, but this is what he realized, is that if you could shoot the cannonball fast enough, it would go so far that the curvature of the Earth would start to matter. The cannonball in this case got all the way to here. If you shot it even faster, it would go, maybe most of the way around the Earth, all the way to here. So here he went from like the North Pole to the tip of, the southern tip of South America. And finally, if you shot it fast enough, what would the cannonball do? It would leave the cannon, it would go sideways, and it would, be falling towards the Earth, but the Earth would be curving away from it at exactly the same rate that the cannonball was falling towards it, which means the cannonball would never actually get any closer to the Earth. It's going around the Earth, and it's falling towards the Earth, but it's not getting any closer because of its sideways motion. So the cannonball in this case is in orbit. This is what orbit actually is. Orbit is something falling under the force of gravity towards another body, but never actually getting there because it's moving sideways too quickly. So, yeah, this is the illustration that was actually in the Principia of this idea of Newton's cannon. So the ball is carried along in its orbit because it's got inertia and it's moving sideways. Remember Newton's first law. An object at rest or in motion, well, in this case, an object in motion will stay at rest or in motion, straight line, constant speed, unless acted upon by an outside unbalanced force. So, yeah, the ball has inertia. It's going sideways. It wants to keep going sideways, in a sense, but gravity is going to start curving it. That's what's happening. So think of the cannonball first, going around sideways like this, and then realize, well, that's actually exactly what the moon is doing. The moon is going around the Earth. The Earth is pulling on the moon with its gravity. The Earth is trying to pull the moon into the Earth, but the moon's not getting any closer. It's actually getting a little bit further year after year, but that's a different story. The moon's going, the Earth is pulling on the moon, trying to bring it closer, but the moon keeps going sideways because the moon was already moving. So, yeah, the moon in orbit around the Earth is the same thing as, Newton's cannonball going around the Earth. So this is a joke that I love, and I teach all of my physics students on the first day of the year. What did the Dalai Lama say to the hot dog vendor? He said, "Make me one with everything." So the idea of being made one with everything, physics is a very unifying science. So what do I mean by that? So think of Newton sitting under his tree in a contemplative mood. An apple falls, he notices it, and look, hey, way off in the distance, he can see the moon out there. So Newton is not the first person to realize that apples fall from trees. Everyone knew this. This is patently obvious. Apples fall from trees. He's also not the first person to know that the moon goes around the Earth. Yeah, for thousands of years, we realized that's what was going on. The genius of Newton is realizing that these are actually the same thing. The apple falling to the Earth is the same thing as the moon going around the Earth. Not even that they're similar. They're really actually the same thing. It's gravity doing both things. So this is the idea of being made one with everything and physics being a unifying science. So philosophically, in the history of human thought, this is a huge idea because up until this point, everyone thought, okay, we have a set of rules for the things that are happening down here on the Earth, and there is a different set of rules for everything happening up there in the heavens. So apples falling from trees, okay, well, there's rules about that. Apples fall from trees. We've got a rule for that. The moon in orbit around the Earth. By this time, Galileo had seen moons in orbit around Jupiter. The planets going around the sun, all of these things. Those follow their own set of rules, right? The genius of Newton is realizing, no, they're all following the same rules. They're following the law of universal gravitation, and they're following Newton's laws of motion. And there's one set of rules that governs everything in the universe. And once you know that one set of rules, you start to see that there aren't completely different phenomena going on all over the world, all throughout the universe. There's just one kind of thing happening. And you become one with everything once you know those rules. And those rules are physics. And astronomy is just the physics of big things. So here is La Pulga Atomica, the atomic flea. This is Leo Messi, a fairly short person for one of the most famous athletes in the world. So Leo is going to kick the football on the left. You Americans would call this a soccer ball. Most of the world would call this a football. And on the right, he's going to kick a bowling ball with the same amount of force. So which one's motion will change more? You don't need to have had any physics to realize that the soccer ball's motion is going to change more. That's just intuitive, and your intuition is correct in this case. The reason why is the bowling ball has more mass, therefore it has more inertia, therefore the bowling ball is more reluctant to change its motion. The same amount of force on both of these objects is not going to affect the bowling ball as much because it has more mass. So intuitively, you know that is correct. And this leads us to a wonderful, wonderful idea. F equals ma. Force equals mass times acceleration. This is Newton's second law. Force equals mass times acceleration. It is such a simple little equation, and yet it explains so much of what's happening in the universe. At any given instant in the universe, this is pretty much all that's happening. Forces are accelerating masses. Start with that idea, and you can explain so very much. So now that we have this mathematical relationship, we can get a little better at this. So now we know that the bowling ball has 16 times the mass of the football. So if Leo Messi puts the same amount of force on both objects, how will their accelerations compare? Well, we already know that the football's acceleration will be greater, but now that we have the math, we can figure out that the acceleration of the football will be 16 times that of the bowling ball. Because if F equals ma, then A equals F over m. So the bowling ball has 16 times as much mass, therefore the bowling ball has 1/16th the acceleration of the football. So let's compare Newton's second law to Newton's first law. So Newton's first law says that when there is no net force on an object, so when F sub net, the net force, equals the sum of the forces, that's what net force means, equals 0, the object is in mechanical equilibrium or uniform motion. So if it's not moving, it will continue to not move. If it is moving, it will move in a straight line at a constant speed. So here we have an image of a car going in a straight line down the road at 30 miles per hour. Ignore the fact that there's friction and air resistance and all these things. Just imagine this car, it's just in neutral. It's just coasting. And it's going to keep going 30 miles per hour in a straight line. So if we put a net force on this object, its motion is going to change. Either the direction that the object is moving in will change, or its speed will change, or both of those things will change. So an object's speed plus its direction is called its velocity. Velocity is speed and direction. If either of those things or both of those things changes, then the object is said to be accelerating. That is what acceleration is. So when you step on the accelerator, which is another word for gas pedal, your car accelerates. Okay, you all knew that. As far as a physicist is concerned, when you step on the brake pedal, your car also accelerates. It doesn't accelerate forward, which is what happens when you press on, the accelerator. It accelerates backwards. Even if you're moving east and you hit the brakes, your car is accelerating. It's accelerating west as you move east. That's a weird idea if you haven't had physics, but that's how it works. Because your speed is changing, and if your speed is changing, you are accelerating. Perhaps even stranger, according to a physicist, your steering wheel also accelerates your car. So even if your speed stays the same, you're going around this turn here in this picture, and maybe you're going 30 miles an hour the whole time. If you change this, if you turn the steering wheel, the direction changes. And velocity is speed plus direction. So if your direction changes, your velocity changes, and that is acceleration. So as far as a physics teacher, a physicist, as far as the subject of physics is concerned, your gas pedal, your brake pedal, and your steering wheel are all things that accelerate your car. Seems weird, but that's how it goes. So yes, F equals ma, therefore A equals F over m. So look at these two expressions here, A equals F over m, and A equals F over m. So we say that the acceleration is directly proportional to the force. A is equal to F divided by M. So what that means is if F gets bigger, A gets bigger. We also say that acceleration is inversely proportional to the mass. A equals F divided by M. So what that means is if M gets bigger, A gets smaller. So you may know this from your day-to-day life. So imagine you're pushing a shopping cart. The shopping cart is empty. You put a force on it, and the shopping cart accelerates. And the bigger the force on it, the faster it accelerates. Now imagine you're putting about the same amount of force on the shopping cart, but this time it has a bigger mass. So how will it accelerate? Well, A equals F over M. If F is the same and we're dividing by a bigger M, then A will be smaller. So that's how that works. Now, in either case, empty shopping cart or full shopping cart, as long as we can ignore air resistance and friction, if you push the shopping cart, you get it moving, and you stop pushing on it, the cart is going to coast in a straight line at a constant speed because of Newton's first law, the law of inertia. So we went from using the second law here to get this cart moving to now there's no, we put a net force on it. Now the cart is accelerating. If you take away all of the forces, what does the cart do? It continues to coast, straight line, constant speed. Aristotle was wrong. You don't need a violent imposed force to keep it moving. So a final thing here is mass is not weight. This is commonly confused before you start taking the physics, or in this case, you're taking astronomy and getting a crash course in physics. Mass is a measure of inertia and has units of kilograms, kg, and mass is the measure of the body's reluctance to change its motion. Weight is different. Weight is a force. It is different than mass, and weight has units of newtons, which is an N. So astronauts experience weightlessness. No one ever experiences masslessness. So here we have astronauts. I don't know. Maybe they're on the ISS, and they're having fun. They're playing around with some fruit. Now everything in this image is weightless at this time. Everything's just floating around. Because it's in orbit, we can say that it's weightless. None of these things are massless, however. So we can see this astronaut here. She's pushing with a little force on this apple. She's going to change this apple's motion. The apple will begin to accelerate as she puts a force on it. If she were to put that same amount of force on this dude back here, he will also accelerate, but he's not going to accelerate nearly as much as the apple would under the same amount of force, because if F equals ma, then A equals F over m. So in that case, you're dividing by a much bigger m. This guy's mass is much bigger than the mass of the apple, so he doesn't accelerate nearly as much. So to review very quickly, what was Isaac Newton's famous book explaining the laws of motion and of gravity? This was the Principia. What was the thought experiment that Newton did to explain how gravity kept things in orbit? This was Newton's cannon. Wonderful idea. This is what orbit actually is. And finally, what is Newton's second law of motion? F equals ma. So, yeah, the pictures you should associate with this are Leo Messi kicking a football on the left and Leo Messi kicking a bowling ball on the right. And given the same amount of force on both objects, they will have different accelerations because they have different masses. But that's it for this part of the slides. Hopefully you're finding this helpful.